In this video, we're going to look at graph recognition. We're going to start off with linear graphs. As the name suggests, linear graphs are just straight lines. The easiest ones to see are the vertical and the horizontal lines. So for example, now this one here would be x is equal to 4. So a vertical line has an equation, x is equal to 4. If it was just here, x is equal to 6, x is equal to minus 3. We could have now a horizontal line, and a horizontal line would be y is equal to some value. So for example, if I had a horizontal line just here, y would be equal to 2. So these are the most basic straight lines. If we look at the red one, this is y is equal to x. With linear graphs or straight lines, we only have the first power on each of these variables. So this is y to the first power and x to the first power. So it wouldn't be x squared, it wouldn't be y cubed, it's just y is equal to x. So that's that line just there. Often these are written in the form y is equal to mx plus c, where m is the gradient of the line and c is the y-intercept. So we could look at this one now and we can see that this has a gradient of 1 and a y-intercept of 0. If we looked at the other ones, we could work out now the gradient of each of these and substitute it into this particular equation. I've done a video on this particular form. All we're looking at doing in this one is graph recognition. Another way these can be written could be ax plus by plus c is equal to 0. So that's another form. Generally speaking though, we would have this. So let's look at some straight lines. Y is equal to 3x plus 1. This is going to have a gradient of 3 and a y-intercept of 1. So this is going to be a steeper line than y is equal to x, as we just have a gradient of 1. We could have now y is equal to minus 2x minus 4. This has a gradient of minus 2 and it has a y-intercept of minus 4. So these two here are examples of now negative gradients. They're going down. So if it's a positive gradient, it will be going from the bottom left to the top right. We can see that with all of these. If it's a negative gradient, it will go from top left to bottom right. So nice, straightforward, straight line graphs. I'm going to draw a couple of graphs. I'm going to do y is equal to, and I'm going to have now 2x plus 1. So if I wanted to draw that, I've got a gradient of 2 and a y-intercept of 1. So if I locate that, that is going to be now 1. That's where it's crossing the y-axis, and it's got a gradient of 2. So it's telling me now that for every 2 it goes up, it goes 1 across. So if I go up by 2, I will go to 3, and I need to go across by 1. If I now go up by 2, I need to go across by 1. So that's going to take me to this point here. Once I have a couple of points, I can draw now the line straight through this. So just drawing the line, it will look something like so. So whilst this isn't massively accurate, it gives us some idea. In the video on graphing straight lines, we'll look at a more accurate way of doing each of these. So I'm just going to write out a few straight line graphs here. So for example now, y plus x is equal to 5. That would be a straight line. If you wanted, you could rewrite this as y is equal to minus x plus 5. So we'd have now a gradient of minus 1 and a y-intercept of 5. So that would be coming down somewhere like so. If we had now, for example, y is equal to 1/2 x minus 3, we've got a gradient of 1/2 and a y-intercept of minus 3. If we had y is equal to 4 minus 5x, we could rewrite this. Y is equal to minus 5x plus 4. We have a gradient of minus 5 and a y-intercept of positive 4. So linear graphs, straight line graphs, we only have the first power. We don't have any multiples, so we wouldn't have x times by y. It's just now y to the first power and x to the first power, or these straight lines. Let's now look at quadratic graphs. Quadratic graphs are called parabolas. So these are generally when we have y is equal to ax squared plus bx plus c. So this is a quadratic graph, and our highest power is an x squared term. This is the easiest one to see, the red one. This is the standard graph of y is equal to x squared. We can see it's symmetric. All of these parabolas are symmetric, and it's symmetric about the y-axis. So if we built up a table of values, we would see now the following results. So if I put in values of x and the corresponding y values, and we'll just put some in. Let's grab up the pen. Let's do now 0, 1, 2 and 3. So for x, we would have now 0 squared is 0. If we have 1 squared, that's 1, 2 squared is 4, 3 squared is 9. And we can see 1, 1, 2, 4, then we'd have 3, 9. Remember, for negative numbers, when we square a negative number, we get a positive. So we can see minus 1 gives us 1, minus 2 is going to give us positive 4, and minus 3 is going to give us 9. So we end up now with this symmetric graph. This is a negative quadratic. So this time it's upside down. So we could write a negative quadratic could be minus x squared plus 6. That is an example of a parabola. The highest power of x is x squared. We don't have y squared, we don't have y cubed. We're just looking at x squared. So generally they can be written in this particular form. So if we had now y is equal to 2x squared minus x plus 6, when we went to draw this now, we would have a parabola. So that's what a parabola looks like. It's symmetric, and we'd either be asked to sketch it or construct one from a table of values. When you're drawing it, go ahead and draw a sweeping curve through the points. It's not a case now of getting a ruler and doing the following. So if, for example, now I went to there, it wouldn't be that. It doesn't look like that. It's a smooth sweeping curve. So just putting these on, that's what we want, and then we would do that. That is not correct. Also, if you're doing a table of values, make sure that you're actually having some symmetric graph. So many students do some bits right, get to the negative numbers, and then their graph goes a bit wonky. So for example, now a parabola might look something like so. So students often end up with something that looks like this, nice and symmetric. It comes around there, it comes up, and then all of a sudden it goes down here somewhere. Make sure we're symmetric. So they are quadratic graphs. We call them parabolas. They're symmetric. We call this point the vertex. I doubt you'd be asked that necessarily at this level, and then we can construct them from a table of values, or we can sketch them. They take this form: y is equal to ax squared plus bx plus c. Let's now look at cubic graphs. This is a cubic graph. This is the cubic graph, y is equal to x cubed. So when we're talking about cubic graphs, the highest power of x will be x to the power of 3. If we look at this one now, what we're going to have, we could build up a table of values, is the following. We know that if we cube a negative number, it's going to give us a negative answer. So what we're going to have then is the following. If we take 0, 1, 2, and 3, take our values of x and our corresponding values of y, 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. This will get very big very quickly. If we now look at minus 1, if we cube minus 1, we get minus 1. Minus 1 times by minus 1 is equal to 1, multiplied by minus 1 again, and you're going to get minus 1. So cubing a negative number means that we're going to have this part just here coming down and being negative and getting very big very quickly. So minus 2 is going to give us minus 8, and minus 3 is going to give us minus 27. These generally can be written in the form y is equal to ax cubed plus bx squared plus cx plus d. Again, at this level, that might not be introduced, but an example might be y is equal to 3x cubed plus 6x minus 2. So in this particular occasion, b, the x squared term, we don't have one, that would be perfectly fine. That is a cubic equation. We can see the highest power on x is going to be x cubed and y is just to the first power. So here are some cubic equations. With the positive one, it's going to start down here in what we call the third quadrant, or if you like, bottom left, and go out the first quadrant, which is top right. A negative cubic equation will start top left, or the second quadrant, and leave bottom right, which is the fourth quadrant. Just labelling these up, this is the first quadrant, this is the second, this is the third, and this is the fourth. So cubic equations, again, a sweeping curve. Don't be tempted to connect these with straight lines, it should sweep through. We can see here this one goes through the origin. So recognising cubic graphs, it's highly unlikely that you'll have to do anything beyond here. You might have to plot some values now, or I say find some values, plot the points and draw that curve. Okay, let's go ahead and move on. Exponential graphs. Exponential graphs can be written in the form y is equal to a to the power of x. A is going to be greater now on here than 0, and it can't be 1. You won't be tested too much on these, but it is important to look at some of the key points. So we've got some graphs here. Unless they've been transformed, they will all go through the point 0, 1. If we think about this now, 2 to the power of x, let's take now 2 to the power of 0. So 2 to the power of 0 will give us 1. If we took 3 to the x, 3 to the power of 0 is going to be equal to 1. So we can say when x is equal to 0, y is going to be 1. And we can see that just here. These now, we have positive graphs that grow very quickly from this point here. We also have what we call an asymptote. On this particular graph, we can't see it, and it's the x-axis. It can never now, these graphs can never be equal to 0. So with this one, this would represent, for example, decay. So if we started it at 0 hours just here, it would get smaller and smaller, but it would never get to 0. If you think of a bar of chocolate and you have half each day, you have half the first day, you have half of a half, which is a quarter, half of a quarter, which is an eighth, half of an eighth, which is a 16th, and so on and so forth. You're going to be finely chopping that up, but it will never get to 0. It will tend to 0. That, highly unlikely to be asked, but that's why it's important that we have this asymptote. It says it can't go below the line. In the same way, if this one has been transformed, we would put our asymptote just here, and it could never now go below 1. You'll look at this later in your studies, but this gives us some idea of an exponential graph. So exponential graphs, and this is what we have. So let's say we did now, and we'll have a look at one of these. Let's say we did y is equal to, and I'm just checking the ones that we've got. We'll do now y is equal to 3 to the power of x. So if we think about this now, y is equal to 3 to the power of x. We can take values of x and find the corresponding y values. So just putting this in a little table. Let's go for some positive numbers. Let's start from 0. We will take 1, we will take 2, we will take 3, and we'll take 4. We will even look at some negative numbers. These are quite interesting, and if you are more interested in these for now, I appreciate that this is quite hard, but we'll give it a go. So this is going to be my x and my y. So 3 to the power of 0, 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. 3 to the power of 4 is 81. We can see that this is going to get very big very quickly. The larger this number, the steeper this curve is going to be. If we look now at minus 1, 3 to the power of minus 1 is the same as 1 over 3 to the power of 1. So that's going to give us now 1/3. 3 to the power of minus 2 is going to be 1 over 3 squared, which is going to give us 1 over 9. 3 to the power of minus 3 is going to be equal to 1 over 3 to the power of 3, and that's going to give us 1 over 27. So we can see for negative values now, negative values of x, this is going to get closer and closer to 0. We say it tends to 0, but it doesn't ever equal 0. Remember, this is just using the rule a to the power of minus m is equal to 1 over a to the power of positive m. So these are exponential graphs, and they're generally used to model growth and decay. So a nice example might be if you had a car. If you had a car, and we'll put this on, and we started, and this was the time in years. So if we put now t, so this is t years, and this is going to be the value. So let's put on the value. We could see, let's say it started at £9,000, and we'll say that this is thousands, so thousands of pounds. We might have something like here, so we'll start at 9. So when it was first purchased, it would be 9, and then it would come down, and it would form now an exponential decay model. So let's just come around here, and it'll look something like that. Obviously, these models over time kind of don't really hold, because after, let's say we had 10,000 years, it would tell me that it is 0.0000 of a penny. But that gives us some idea. On the other hand, if we were growing bacteria in a lab and it was growing at an exponential rate, we might start with 3 and it might do something like so. So as the time increases, this gets very, very rapid and very quick. So they are exponential graphs, and we've looked at a bit beyond what you'd be expected to do. Okay, let's now look at reciprocal graphs. Reciprocal graphs can be written in the form y is equal to a over x. A is just a constant, so it's a number we're given. This is the nice straightforward one here. Y is equal to 1 over x. So essentially we're looking at something that's inversely proportional. So if I think about a table of values, we're going to have our table of values, and we'll write this in for y is equal to a over x. We can see what's going to happen. So if I put this on, we're going to have the following. So let's now do that, and we will have now, let's start here. Okay, I'm going to introduce 0, I'm going to have 1, I'm going to have 2, and I'm going to have 3. We'll even put 4 on. Let's look at minus 1, minus 2, and minus 3. This is an important point. Division by 0 is undefined. That means that we can't have now a value here, and we put in, technically I could put in positive infinity. Well, I suppose I could put in negative infinity, but essentially what we end up with is an asymptote. The asymptote is going to be now the y-axis. We have a vertical asymptote, and also we have a horizontal asymptote. And the horizontal asymptote is the same reason as we had before in the last. So the asymptotes are hidden by the axis in this case. It's just telling me I can never go on this side of the y-axis less than 0. And on this side of the axis, now above 0. So if we look at some of these, let's put these on. So 1 over 1. So when x is 1, y is going to be 1. 1 over 2 is going to give me 1/2. 1 over 3 is going to give me 1/3. 1 over 4, we're going to end up now with 1 over 4. We can see that this is getting smaller and smaller and smaller. So 1 over 1 million is tiny. It still isn't 0 though, and that's why we have the asymptote. 1 over minus 1 is going to give me minus 1, and we can locate that point just here. 1 over minus 2 is minus 1/2, and that's going to be the point just here. We've got 1 over minus 3, which is minus 1/3, which is going to be the point here, minus 1/4, and so on and so forth. So that now gives us a reciprocal graph. If we look at another graph, we might have 2 over x. We might have 3 over x. So if I write this here, let's go ahead and do that. So we might have y is equal to 2 over x. We might have y is equal to 3 over x. We might have y is equal to 4 over x. We might have y is equal to 5 over x. We might have y is equal to 6 over x. We might have y is equal to 7 over x. We might have y is equal to 8 over x. We might have y is equal to 9 over x. We might have y is equal to 10 over x. We might have y is equal to 11 over x. We might have y is equal to 12 over x. We might have y is equal to 13 over x. We might have y is equal to 14 over x. We might have y is equal to 15 over x. We might have y is equal to 16 over x. We might have y is equal to 17 over x. We might have y is equal to 18 over x. We might have y is equal to 19 over x. We might have y is equal to 20 over x. We might have y is equal to 21 over x. We might have y is equal to 22 over x. We might have y is equal to 23 over x. We might have y is equal to 24 over x. We might have y is equal to 25 over x. is equal to now 1 over 4x. This is just saying that it's 1/4 of 1 over x. We might see this in the form, less so now, but more so later in your studies. For example, xy is equal to 5. We could rearrange this and write this as y is equal to 5 over x and then deal with that. In the video on graph transformations, we will spend some more time looking at these, but essentially if you're asked to just fill in a table of values, this is what we'd have. So we can see that we have this sweeping curve like so, and then to the other side. It's important that you appreciate those asymptotes. Okay, let's look now at circles. At this level, generally speaking, we would write the equation of a circle as x squared plus y squared is equal to r squared, where r is the radius squared. This gives us a circle, so we'll have a circle, we will have a centre of 0, 0, and we'll have now a radius which is going to be r units. That's what this is. So if I said now x squared plus y squared is equal to 9, this would give us a circle. It would have now its centre at the origin, and it would have a radius of 3. If we look, that's the blue one on here. So if we look at some points, this point here is going to be 3, 0. So if I square 3, I get 9. If I square 0, I get 0, which equals 9. If I take this point just here, I've got 0, 3. X is 0, 0 squared is 0, y squared, 3 squared is 9, and that works out. This point is minus 3, 0. If I square minus 3, I get 9. If I square 0, I get 0. And again, it satisfies this equation. This one is 0, minus 3. 0 squared is 0. Minus 3 squared is 9. And we can see it here. So that is what we have. The killer mistake pupils make is that they often say that this is the radius. Remember, this is the radius squared. As you move your studies on, you'll see that this is simply a case of Pythagoras' theorem. So if I had x squared plus y squared is equal now to 16, centre 0, 0, radius of the square root, and it's the positive square root of 16, which gives us 4, and that's the orange one just there. So for example, if you saw now x squared minus 25 plus y squared is equal to 0, we could rearrange this, x squared plus y squared, and adding 25 to both sides, we can see this is a circle, centre 0, 0, and a radius of 5 units. If we had x squared plus y squared is equal to 8, the radius would be the square root of 8. If we were asked for this in third form, it would be 2 root 2. If you've done work on thirds, you can see that that will break down to the root of 2 times by the root of 2 times by the root of 2. Once you've got to this stage, that's a skill that generally you would have. If we move this on slightly, and this is extending away from the particular syllabus, we can write the general equation of a circle as x minus a all squared plus y minus b all squared is equal to r squared. This gives us a circle with a centre a, b and a radius again of r units. So this is a bit beyond the scope, but if we look at this one right here now, we have the centre of 1, 0 and we have a radius of 1. So we could write this as x minus 1 all squared plus y minus 0 all squared is equal to 1 squared. So just tidying that up, we'd have x minus 1 all squared plus y squared is equal to 1. And it kind of, you now realise why we just have x squared plus y squared is equal to r squared, because it's x minus 0 all squared plus y minus 0 all squared is equal to r squared. So that is the equation of a circle. You might be asked to draw one, you might be asked to just give an equation from a basic example where we have the centre at 0. So there we go. Let's now move on, and what we're going to do is recognising graphs. So we've got here 5 different graphs. The only one we don't seem to have is a circle. So a typical exam question, it might say now label these up with the equations here. So let's have a look. Let's start now with this one. This is a straight line. So what we're looking to do is find an equation that matches the straight line. I know it's not going to be this one. We've got now 2 over x. That's going to be a reciprocal graph. If I look at this one, we've got an x cubed term. For it to be linear, we've got y to the first power and x to the first power. The only one that does that is the one at the bottom. And we can just go ahead and write that is y is equal to 1 minus 2x. Y-intercept of 1, gradient of minus 2, and it looks something like so. This one here is a parabola. So this is a quadratic graph, and we're going to have the highest power of x as x squared. I've only got one choice just here, so it's going to be that one like so. So we can see now, out of interest, if x was equal to 0, y would be equal to 2, and we can see that point here. Okay, let's go ahead and look at the next one. This now is an exponential graph. So this is modelling now exponential growth. This is going to be of the form y is equal to a to the x. So it's going to be y is equal to 4 to the power of x. And if we look at that now, we can see that when x is 1, y is going to be 4. If we now look at this one, this is a cubic equation. So we know we're going to have a cubic, so it's going to be to the power of 3. And this is y is equal to 3 lots of x cubed. So the standard x cubed curve has been transformed with a scale factor. Again, we will look at the scale factors when we come on to graph transformations. That leaves one more, 2 over x. This is a reciprocal graph. So if we had 1, it would be 2. If we had 2, it would be 1. If we had 3, it would be 2/3. If we had 4, it would be 1/2. And that's what we end up with. So graph recognition, we're looking now at some basic equations of graphs and their shapes. Linear graphs are straight lines, first power for x and y. Quadratics, ax squared plus bx plus c. These are parabolas, they're symmetric, and the highest power of x is x squared. Cubics, these have a cubic term as their highest power. We have now this sweeping curve. We can see these in the form ax cubed plus bx squared plus cx plus d if we like, but generally speaking, you'll be asked to plot the table of values or recognise the graph. Exponential graphs model growth and decay. We've got y is equal to a to the x. So it's now the power that's the unknown, the variable, or the thing that's changing. We have asymptotes, and the asymptote here will be the value that it can't fall above or below, and unless it's transformed, that is now the x-axis. Reciprocal graphs, 1 over, or a, where a is just a number, 2, 5, 10, is just a constant. We have a vertical asymptote, as we can't have division by 0, and we have a horizontal asymptote, as this can never be equal to 0. We can keep cutting that bar up into smaller and smaller parts, but it's going to end up now tending to 0, not actually getting to 0. Then circles, x squared plus y squared is r squared. That gives us a centre 0, 0 and a radius of r. Remember, this is the radius squared, and then we looked at just some recognition.